and I'm going to share my work understanding data importance in machine learning attacks. Does valuable data pose great harm? This is a joint work with Michael and Zhang, and I'm excited to discuss how data importance interact with machine learning attacks. So machine learning has come a long way in recent years, and it's now a major force driving innovation across various fields. You can't turn around without hearing about AI these days. It seems to pop up everywhere. Just think about ChatGPT. It's helped us to chat smoothly with machine. Then there's Copilot, which generate high-quality code faster than you can say debugging. But behind all this impressive progress, there's one thing that drives it all: data. Good data is like a fuel for this model. The more and better the data, the smarter and more flexible the model became. Simply put, good data make all the difference. But not all data is created equal. When we train the model, there are some data like VIPs. They contribute a lot to the model utility, while others just sit in the background, contributing very little. And to quantitatively measure the contribution of these samples, we use the concept of Shapley value. And this Shapley value represents how much an individual samples contribute to the model utility. If a sample contributes a lot to the model performance, then we call this sample as important data. While if a sample contributes only a little, then we say it's less important. And when we train model using this important data, and we can get a model with much better performance compared with the same model, but trained with less important data. And to illustrate this, I sorted a data set and trained two models, one with the most important samples and one with the least important samples. As we can see, the performance gap is significant. But what about security? How does this data variation impact their vulnerability? This problem remains largely unanswered. While data plays an important role in machine learning ecosystem, when we talk about vulnerability, we mostly talk about the model itself. Like sometimes people will say overfitted models are more vulnerable to membership inference attack. But even within the same model, we can see different sample has different level of vulnerabilities. Take a look at this picture. While this blue section represents member data, the range of vulnerability is very huge. And take a look at these two areas marked by red circle. They are both members, but their vulnerability is vastly different. So this raises an interesting question. Can we use data importance to illustrate this difference? Or in other words, are high-value data also more vulnerable to machine learning attacks? And understanding this problem have some real-world implications, like take medical diagnostics as an example. Patient records with rare but crucial symptoms are considered more important. And if these patient records are more prone to attacks, it can cause breaches that affect patient privacy, and it can cause discrimination or even drive up insurance premiums. And in this talk, we take membership inference attack as a case study. And briefly speaking, membership inference attack aim to infer whether the target sample is used to train the model. So to test the inference of data importance, we first train our target model, and then then sort the training data set by its importance. Then we run membership inference attack on each subset with different level of importance. As shown in this figure, we can see that samples with higher importance are more vulnerable to membership inference attack. So what does all this mean? Well, there's a strong connection between how important a sample is and how likely it is to be attacked. But we don't stop here and want to ask, can we use these findings to derive stronger attacks? And actually, the answer is yes. Let's take the simplest membership inference attack to illustrate, where the attacker uses loss to determine whether a sample is used to train the model. So, and typically, member samples have lower loss, so the attacker can set a threshold and anything with a loss lower than that threshold is marked as member. But this method works and has very high significant rate. The problem is that not all member samples have lower loss compared with non-members, because there are some low-important samples that are hard for model to learn. So even after training, they have higher loss compared with those non-members. And this makes it tricky to tell these members apart from non-members. And in fact, there are even some non-members that have lower loss compared with members, because these non-members are of high importance, and they can be easily learned and end up with better membership metrics. So how can we improve on this? One potential strategy is to compare samples with each other of a similar difficulty level, or in other words, we introduce sample-specific threshold. And when we want to determine the membership status of a high-importance sample, we just compare it with other high-importance samples. And we do the same for low-importance samples. They have their own threshold. Following this intuition, we introduce sample-specific threshold, but in a consistent manner, because we want to incorporate this to existing framework. And we keep the threshold the same for the whole dataset, but we tweak the membership metrics. We introducing an important related factor. And the results show that with importance calibration, the membership inference attack has better performance. In summary, we found that high importance data is more vulnerable to membership inference attack, and by setting sample-specific threshold based on importance, can design stronger attacker, can make attacks even stronger. But let's not stop here. Previous research has shown that data vulnerability can shift. There's something called privacy onion effect. It basically says that when you remove the most vulnerable data from the dataset, the next layer of previously safe data now become more vulnerable. As we have already linked the membership vulnerability with its importance, we may want to ask, can manipulating the dataset influence the importance of targeted sample? And that's what we are going to explore next. A detailed example of privacy onion effect is shown in this figure. We first train a machine learning model, and we discard all data with vulnerability higher than the threshold. Then we retrain the model using the remaining data. And ideally, none of the remaining data should have vulnerability higher than the threshold. But as we can see in this figure, there were samples that used to have lower loss now surpass the threshold. We run the same experiment on again, but this time we're focusing on importance instead of vulnerability. We found the conclusion still holds. If we remove the most important samples, previously less important samples start gaining importance. But it might be a bit earlier to say this conclusion, because changing the size of the dataset could also explain the shift in importance distribution. So we conduct a controlled experiment where we either remove the most important or least important sample from our dataset. And the conclusion still holds. If we remove the most important samples, less important samples start gaining importance. And this actually gives us a powerful intuition for developing stronger attacks. If we can manipulate the dataset to influence the target sample's importance, could we take some samples that were initially low importance and boost its importance to make it easier target for membership inference attack? But this is not easy because there's no uniform like guidebook or framework for it. So we decide to do some bit creative and try some ad hoc method. Showing this figure, we mark the target sample with a black square. To increase its importance, we try some more sneaky approach and duplicate these samples multiple times, but with consistently incorrect label. The reason we do this is because when models see so many incorrect versions of the target sample, the models start to treat this sample as outlier. And outlier tend to grab models' attention, making these samples more influential or more important. And we test this idea by duplicating 50 samples 16 times and recalculate the importance. As we can see in this figure, 45 out of 50 samples have an importance gain, with an average increase of 53%. In the same time, the importance of untouched samples are barely influenced. This is actually a classic membership poisoning attack first proposed by Zhang et al., and their work shows how effective this method can be. So, actively manipulating the importance of target sample could be a powerful tool for crafting stronger attacks. In summary, we identify privacy artifact in the data importance domain, and we show that actively manipulating sample importance could be a powerful tool for designing advanced attacks. We have more interesting findings that show the connection between data importance and vulnerability in our paper. Feel free to check it if you are interested. And to wrap things up, we have shown that high importance samples are more vulnerable to certain attacks, and such as membership influence attack. And with this knowledge, we could introduce sample-specific criteria or sample-specific metrics like importance to improve the attack performance. And we also show that we can actively manipulate the importance of certain samples to make them more vulnerable. Thank you for your attention, and I'm happy to take questions.
Thank you for your great presentation. Do we have any question from the audience?
Hi, thank you for your talk. I'm Elisa from Michigan. I have a question about the matrix for data importance, because you were looking at the Sharpley matrix to quantify how important a data is. I wonder if you experimented with other like learning-based metrics or like data diversity-based metrics and see if that affect the results.
Do you mean that or try different methods to evaluate the importance of a sample?
Yeah.
Yeah, actually, I have tried some different method and find that Shapley-based method is most efficient. And for other kind of method, even they can identify a high important sample and less important samples. But when you train models with these two sets of samples with the same number, the performance gap is not that significant. And we found that a Shapley value-based method could give the best results. So we decided to follow that.
Thank you.
Thank you.
Thank you. Thank you for the work. I think it's very insightful. My question is, the vulnerability, I think, is not only related to the training data. When evaluated, the vulnerability, it's also related to the test data you're using. So for this method, is there any relationship between like the importance of training data points and its relationship between these data points and test data? Is there any consideration on this aspect?
Well, that's a good question because when we calculate the Shapley value, we also need a validation data set. So if the validation data set is vastly different from the target domain, then maybe the results of Shapley value, the importance is not that meaningful. It cannot directly transfer to different domains, I think.
Okay. Yeah, thank you very much. And also I have one additional question. So in lieu of in the data point space, have you considered to extend your method to feature space? For example, to identify which feature could be more vulnerable if you manipulate, for example, add extra data points into the data set?
Yeah, actually, I saw that some features are more vulnerable than others, but it's not directly related to data importance. I used to have a work show that we can modify different part of the features, and it could lead to different poisoning effect. That's true, but but I think it's not related to importance. Maybe we need different metrics or method to determine the importance, and the choice of this importance should can have some influence on the conclusion.
Okay.
Thank you.
Thank you very much.
Thank you. Let's thank our speaker.